If there's one thing guaranteed to derail a perfectly good day's coding, it's words like header file not found. You ever experienced this? You want to get a job done in some random language, and you install a package, and that depends on another package, and that package happens to build a C library that won't build on your machine. And so, bang, cancel your plans for the day, whatever you thought you were doing. Today, you accidentally need to become a C build expert if you want to get the job done. It's happened to me countless times. It's not C that bothers me, it's becoming a build systems expert that bothers me. And it seems to happen whenever you want to build something that uses a native package. And it happens because, to paraphrase this week's guest, C's portable, but it's not completely portable. It's just a fact of life. It's something that comes up all the time. And some package managers are better or worse at hiding that fact from you. JavaScript, to pick on a victim, JavaScript just seems to wrap the problem with the words no jip half the time for me. Brew on OS X seems fairly reliable at this, but they only have to deal with one operating system. Python used to be bad at it, and then it got the wheel mechanism, which seemed to solve the problem, but it really just pushed the problem upstream to package developers, which is not ideal. Making C truly portable across machines, across operating systems, it's hard, and it affects us all eventually, even by dependency. And there's only one project I know that's really bit the bullet and tried to solve this issue, and that's Zig. So joining me this week is returning guest and my favorite Zig expert, Loris Cro, to talk about Zig not as a language, but as a cross-platform build system. We touched on this a bit the last time he was in the studio, but this week we're going all the way down. And along the way, we pick up some interesting facts about how this might solve an exponential growth problem for the Python community, how you actually do compile C reliably across all the things, and why Loris is working on a new Zig-based static site generator. I'm your host, Chris Jenkins. This is Developer Voices, and today's voice is Loris Cro. Joining me again as a returning guest, it's Loris Cro. Loris, how are you?
Hi, Chris. I'm pretty good. A bit hot. It's summer, but yeah.
Whereabouts are you in the world that's so hot?
I'm in northern Italy, and it wasn't all that hot until like a couple weeks ago, and then it suddenly got really hot.
I have a holiday booked for Rome in like the middle of the summer, and I'm not sure that was a good idea.
Oh, well, dress lightly then.
Yeah. Anyway, whilst the travel podcast is a completely separate franchise, let's talk tech. The last time we spoke a lot about Zig, the language, right? And a bit about the kind of shadow side of Zig, which is the build infrastructure, which you have had to face to live in the world of C. And I thought that would be an interesting topic to dive deeply into. And of all the angles you've been looking at it from recently, Python. What possible link does a C replacement / variant have to the world of Python?
Well, I think that the main link is that if you think about it, Python... Okay, so here's a claim. From my perspective, one of the biggest things that Python has accomplished was democratize access to C libraries. There's a lot of C libraries out there that are very interesting and do complicated things, powerful things. But if you were to use them from C, you would have to be able to build them and to be able to write C. And not everybody is able to do that. But instead, Python can often give you an interface to these libraries. So you don't think about it in those terms necessarily. But if you think about like TensorFlow, NumPy, for example, which are like wildly popular Python libraries, well, they have a huge C infrastructure, like plumbing behind them. And so one way of looking at it, or like OpenCV, for example, that's something also that I've done in the past, like computer vision stuff with Python. Yeah. It's much easier doing it with Python than it is using the C thing directly. But that also means that Python one way or another that needs to deal with the intricacies of building C and C++ libraries.
Yeah. I think C programmers listening to this will instantly disagree with you. But I think at the same time, most people aren't C programmers, and they don't build stuff. They don't build C from source, right? We all have package managers like apt-get or stuff to delegate the problem of building C when all I want is the tool.
Yeah.
So what you're saying is Python is the tool for building libraries that you can easily grab hold of.
Well, it's not. I would say it's the tool to access these libraries, and so then the tool, namely Python, has to, or I would say, well, package creators have to concern themselves with building C and C++ libraries, and so Python has to find a solution to make that happen one way or another, which might be relying on system package managers or some other thing. And if you want, we can get more into detail on some ways in which Python does that. But ultimately, that's what Python has to do to give you easy access to C libraries. Of course, as you said, a C programmer might not agree that Python makes things all that more easy because, to be fair, Python has a runtime. There's also some complexity there. It's not magical, but I think of myself like in university, like first year, wanting to try some computer vision stuff out or wanting to do some, NumPy thing. And I could pull that off with Python. I would have not been able to pull that off, at least that easily, had I had to do, the pure C route.
Yeah. I've definitely been in the situation where I've wanted to use something that depends on building a C library. And in the early days of Python, it's been a failure and a misery. I still get that problem with JavaScript sometimes if it depends on Node GIP, however it's pronounced. But these days, Python Wheels, right, to me seems to have largely solved the problem.
I think so. Yes. So the idea is, I had also your same experience, both with JavaScript, both with Python, observing build failures, and also observing the situation become significantly better with the creation of Python wheels. So a Python wheel is basically, the idea is this: you have a Python package that depends on a native code. So could be C source code, could be C++. Sometimes it's Fortran. It could also be something else. And the idea is you would need to have for a user to install that package, then they would need to build that source code for their machine. They would need to compile the C program. So let's use C as an example of this, just to simplify. The problem is building C code is problematic because you, as you mentioned in the beginning, you install the Python package and then your system needs to have a C compiler. It might need to have installed the dependencies of that C project. And, different systems, different Linux distributions do things differently. For example, macOS, Linux, Windows also in turn are different between one another. And so those things have a higher chance of failing, at least compared to instead the approach where the package creator pre-builds these executables for all the target platforms that they care about. So they will have to go through the process of pre-building for x86, 64, Linux, x86, 64, Mac, Windows, ARM, Linux, ARM, Windows, ARM, macOS, etc. Yeah, so it's a lot of work that they need to do. But, once you've built it, and now users can instead download these pre-built binaries. And the Python wheel system basically is a way for making the package manager aware of the presence of these pre-built versions of the original source distribution. So when you do pip install something that depends on, like you try, pip install TensorFlow, your Python package manager will know how to search for pre-built for TensorFlow wheels, hopefully finding one that matches your current platform. Yeah.
Right. So this is the thing I didn't realize because to me, wheel is just this word that shows up when things are magically working. But what's actually happening under the hood is someone has figured out what architecture I've got, pre-built that binary, uploaded it to
package index.
And and I'm grabbing that binary that someone else has had to worry about for me.
Yeah, exactly.
So where does Zig come into this? What's wrong with that system, and what's Zig fixing?
So, well, first of all, let's look at it from an incremental perspective. Like one thing that is nice about Zig is that usually, that's something that we say when we say maintain it with Zig. The idea is like, what can you do to improve things incrementally before diving deeper, maybe? And you could stop at some point and then still get some benefits. So as a starting point, Zig can help you perfect your source distribution, like your build processes. So you as the package author, so not as a normal user, but as somebody who is doing the work to create these packages. Right now, a lot of times people use virtual machines and Docker containers and a bunch of like a matrix of CI jobs to produce those wheels, because with most C compiler tool chains, without taking a lot of care to enable cross compilation, you normally cannot build from Linux to Windows, vice versa, etc. So what they do is that they spin up a macOS machine or a Windows machine, like a CI job hosted on that platform to build for that platform. So building wheels then entails a bunch of CI jobs that all have to happen on different machines, and then you get all your pre-built wheels at the end. One way of simplifying this would be use Zig, and now you will be able to create from just one CI job wheels for all the other targets that you care about. And that should, at least make it easier, simpler, less expensive even, depending on if you pay for your CI or not.
Okay, give me more detail. How does that work? How is it that... I mean, I understand the naive approach of spin up Docker containers, all the different platforms multiplied by all the different architectures, multiplied by all the versions I want to support of those platforms.
Yeah.
What's Zig doing that system has missed out on?
It's doing, I would say, three things. One, it's not defaulting to using system-wide settings. So it has a better understanding of trying to make a compilation process not depend on the state of your system. Because the moment you depend on system-wide things, then that becomes a problem. So one example of this could be that, for example, Zig bundles a bunch of libcs. And usually a C project will depend on the C standard library. So and there are different implementations that depend on the platform that you run. For example, Linux tends to depend on glibc. macOS has its own libc. Windows has also its own implementation. Some Linux distributions, especially the ones that run in containers, like if you think of Alpine, that has become like a very popular Linux distribution for that's very lightweight for Docker containers. Yeah. That one does not depend on glibc. It depends on Muscle. So you need to have these libcs available to you if you want to target those systems. So that's one thing that Zig does for you. Normally, other compilers depend on the one that is installed system-wide in your system and that works on your system.
Oh, right. So let me just check I've got that clear. Zig is actually shipping all those different flavors.
Yeah, all of them, and different versions of them also. Another thing that can be relevant is getting the glibc version right. This is something that maybe people who write Lambda functions occasionally have to face. If you're writing a Lambda function, I think I hinted at this also last time we spoke. So
we're talking AWS Lambda.
Yeah, AWS Lambda, for example. Yeah. And I think the same applies.
Haskell programmer, so we need to be clear about that.
Oh, yeah, you're right. yeah. AWS Lambda. So we're talking about function as a service, basically. And those, when you write one, for example, in Rust, you still have to worry about the libc running on the engine that's going to run your Lambda. And so there is tooling that has been built to solve this problem. So targeting the right libc is a thing. One trick to not have to worry about it is to, spin up an environment like a virtual machine or a container that happens to have the exact libc library that your users will have. But that becomes problematic because as we just mentioned, there's a bunch of different combinations, and it's hard to predict what your users will have. So Zig bundles all of them for you, and that is step one to be able to do cross compilation.
Okay, so step one is to ship some of that matrix onto your computer.
Yeah, exactly. As source code, yes, absolutely. Yeah. Step two is to have access to tooling that is able to create the final artifacts in a format that is supported by the target platform. So an executable on Linux is an ELF file. An executable on Windows is a PE, portable executable file. And every platform has its own file formats. And as part of the compilation process, they also use intermediate tooling. For example, there's a tool called AR that I think stands for Archiver that creates static libraries. So if you see like a libsomething.a file, that's a static library that has that comes from building a project like a C library into a static library that then can be used in a compilation process. And all these things are system dependent. And Zig bundles all of them. So you will have an archiver and a linker that works on Mac, on Linux, and one for Windows. Every time you get a Zig, like you will get all support for all these other platforms out of the box.
Okay. I haven't noticed that Zig is especially large, but that seems like a burden for the size of shipping Zig itself.
Yeah, absolutely. And if you want to know something interesting about this, you're right. It is not trivial to bundle all these libcs. And if you do it naively, I think your thing is gonna, like, if you were to try to package all of them, I think you will be at least in the hundreds of megabytes. We are a 40 megabyte tarball. So the way this works is by deduplication. So this is actually an active, like, how can I say, field of engineering research in the Zig project, meaning I believe we are still working on an even more improved version of this. But the core point is your different libcs will have a lot of definitions and pieces of text that they share. The idea is to basically duplicate them, long story short.
Oh, right. Yeah. Yeah, that makes sense because they're different enough to break things, but not fundamentally different.
Exactly, because they all implement the same interface ultimately.
So how's that done, out of curiosity? Are you like, I can almost imagine you building the tree of similar bits of syntax and compiling the correct libc before you use it to compile something else.
Yeah. So I think the current approach works like this. Okay, as a starting point, libcs are written in C. C is a fairly portable language, not perfectly so. And also there are some different, like, things work differently in different platforms. And those internal mechanics can be different enough to genuinely require different implementations. So C is portable, which helps with this problem, but not perfectly so. And things are different between platforms. So starting from that point, what we do is, I think the way you described it is a good way of looking at it. It is kind of a tree. So we have think of it a directory that contains all the files that are shared by all libcs. There's not going to be a lot of things. Not everything, obviously, will be perfectly shared by all platforms, but simple stuff will be. Maybe think about an algorithm to produce the square root of something, which is in the libc. Like, the square root is going to be at a high level the same between different platforms. So those files go inside the any-any-any folder, right?
Yeah. Okay.
And then we will have all the files that are shared maybe by architecture. So we will have the x86-64 any folder that contains all the things that are shared not by all libcs for every platforms, but shared by all libcs that are for x86-64 architectures. Right. And then you can get more precise, right? So ultimately, at the the leaves of this tree will be the files that are only specific to one architecture or one specific platform. So they will have a well-defined architecture, so x86, ARM, or something else, a well-defined target OS like Windows or Linux or Mac OS, and a well-defined ABI.
Right. Yeah. This almost reminds me of Unison, the language. Mm-hmm. Where you can have different versions of different libraries, and they're sharing at the function level.
I see.
Right? You could almost split all the different libc libraries up into function level stanzas and then assemble it from that. But you're doing something a bit more coarse-grained than that.
Yeah, exactly. We're doing it more coarse-grained, but the plan is to go to more granular levels. So kind of as you're describing, I think there's more nuance because in a C header file, you have, yes, function definitions, but you also have type definitions and some other things that maybe you might want to be granular on or not. But let's just say, long story short, I guess the goal is to kind of be able to basically diff the libs against one another, right? So that you can collect all the common bits, roughly speaking.
And then brew your own flavor on demand.
Mm-hmm.
Yeah. Okay. So that's step 2. What's the third step in your recipe?
Yeah. So let's see. Step 1, don't depend on system-wide settings, and so that your build can be self-contained. Step number 2, we were saying have access to the tooling that is specific to all platforms so that you can target all the platforms. Step number 3 is, let me think about it for a moment. I had this in mind when I said it in the beginning. But step number 3 is, well, you know what? Actually, that might be it in a sense. Like at this point, you have access to the libcs, you have access to the tooling. The source code, like your original project, obviously needs to be portable in its own. Like the C library that you're building needs to be able to support all these target systems, which is usually the case with C, but not guaranteed. But at that point, you will be able to produce a dynamic library. In the case of Python, usually building native code outputs a dynamic library, so a DLL file on Windows, a .dylib on macOS, or a .so on Linux. And that is what Python will depend on. That's what Python will try to load at runtime. And at that point, I think, you're good.
So in shipping the tooling, are we also including shipping all the different kinds of linker?
Yes, absolutely. Oh, yeah.
Oh, God. Okay.
Oh, yes.
Having sweated with just installing one linker for a particular project, just that is quite nice. Okay. So you've bundled and optimized all these different platforms for building. Is that it? Is that now I can expect to do a portable compilation for multiple platforms on a single platform?
Yeah, at that point you will be able to. Yes.
Right.
You know what? Maybe depending on the nature of your project, there might be one last thing that you need to worry about, practically speaking, which is if your library depends. So Zig brings all the libcs. So you need to target macOS, you will have access to the macOS libc header files, and so you're good. But you might also, your C project might depend on some other system-specific library, which will come, out of the box if you're macOS. But you will need to procure that manually in case you're and bring it to your CI project process. So, for example, if you're cross-compiling a Go application, Go depends on a macOS. On macOS, it depends on a macOS framework. I forget the name. I think it's maybe Core Foundation or something. But in any case, it depends on a macOS framework, which is macOS Apple specific name for a macOS C library, basically. And you need to copy paste them those files where you're running your Zig build process, because you will need access to those files. That said, this is as hard as it gets. This is like the most annoying thing you will have to worry about. And at that point, you run Zig build and it works.
Okay, this has made me think of two particular things that have bothered me about being the person that's compiling C because I have to rather than I want to.
Mm-hmm.
The first is, if I'm bundling a third-party library, do I need to bundle the source for Zig to compile it, or can I get away with the shared object?
You cannot get away with the shared object. So if by shared object you mean the if you mean the .so file, so the pre-built like shared object file, no, that is not enough, and you might not even need it. So the other files is what are needed, because the SO file comes into play once you're loading it at runtime. The header files is basically like the interface instructions that tell the linker that everything makes sense, everything is going to work that way, and so that guarantees success when then at runtime you will load that SO file and will try to interact with it.
Right. Yeah, I don't need access to the source. I just need a promise of where I'll be able to find the compiled function.
Exactly.
Yeah.
Sometimes, though, some dependencies will not be loaded dynamically. Sometimes some other dependencies are expected to be linked statically. So you will produce a final SO, but inside that SO, you might have linked in statically another library. In that case, yeah, you need the full source code.
Okay. The other thing that's bitten me so many times with compiling C libraries reluctantly is, and you mentioned this in a way, like that every OS has a different place it likes to store its libraries.
Oh, yeah.
Who hasn't built a C project and been messing around with LD library path, desperately trying to find the right one that will work?
Yeah.
And there was that old Perl-ish script that Larry Wall wrote that would exhaustively search through configure, that was it. That would exhaustively search through your file system, finding C libraries.
Yeah.
Have you got that?
Yeah, you're right. Oh, that is a great point, man. That might be the third point that I was forgetting about.
Okay.
So, your C library to be built by Zig requires you to write a build.zig file. It doesn't have necessarily to be you, but well, somebody has to do that at some point. So you will find C libraries out there already that do have a build.zig file that they already maintain because they have adopted the Zig build system as one of their build systems. Maybe their only build system, or at least one of the few they support, because it's also not uncommon for C projects to support multiple build systems at the same time, because not all build systems work on all systems, on all platforms. So like, I believe that you cannot use make on Windows. And so you will need to use something else.
Yeah, I've seen people using make on Windows because they've installed that thing that makes old versions of Windows look enough like Linux.
I think you might be talking about MinGW. Maybe?
Yeah. I've seen that a lot at banks where they can't update their version of Windows, but they have to have something that looks like Linux.
Yeah. So it's complicated. Thankfully, you don't have this problem with Zig. Like, you can run Zig build on Windows and it just works. You don't have to worry about it. But so, yes, you will need to basically, somebody will have to write a build.zig file, which is the equivalent of a make file or a CMake file type of thing. But the nice thing is that you're not depending on a third-party thing. So like, your C dependency, like your Zig dependency, basically will take care both of compiling and orchestrating the build process. In any case, the thing is, the build.zig script file needs to be written, and it needs to do all the necessary steps to build the C project. And some C projects have some annoying pre-processing steps that need to be run before you can compile them. Configure is one of them, and different projects might have different things. Unfortunately, the point is, Zig cannot, automatically extract and make disappear all the complexity of C projects. Some of it is there, and to get rid of it, you need to put in some effort. That said, it doesn't have necessarily to be you as the person trying to deal with the C library. Somebody has to do it once, and then everybody else can benefit. So, as mentioned, that some projects, some repositories do already have a build.zig file. But another thing that we're doing is, because it is nice, obviously, like if you are looking for something like, I don't know, Sokol, or maybe you're looking at some other like C style libraries that developers are using, maybe for making indie games or like tiny applications with a GUI where they have to face some of this complexity, but they want to make it easy on them. For those libraries, they will tend to have a build.zig file. But for those that don't, from a community perspective, one thing that happens is that people would want them to adopt Zig as a build system, but the project maintainer might not be interested. So one thing that we did in the Zig project is that we created a GitHub organization called All Your Code Base, which is like a reference to
the classic meme.
Yeah, to the classic meme, to the classic zero wing meme. And the idea is that in there, we are basically placing build.zig files for other projects. So you can shop in the All Your Code Base organization and maybe find a build.zig file for a project, for a C library. And so that basically you can use that one. It's already made. You don't have to do any work yourself.
Right. This is reminding me a lot like TypeScript. you want to use a JavaScript project that
Mhm.
doesn't have TypeScript definitions, but there
Yeah.
is a type definition repo that's completely separate.
Oh, yeah.
Yeah.
Yeah. And we even have a build script for Python in there. Maybe we can come back to this later because I think we will want to talk about other things first. But this might be something interesting to come back.
Okay.
Yeah, once we go.
Make a note of that one.
Yeah.
Okay.
Yeah, so we talked about making it easier to pre-build wheels, right? Less Docker, less containers, fewer CI jobs. Just have one machine do all the building.
Yeah.
And at that point, so for people who are not familiar with how Python wheels work, you then ultimately generally speaking, your final output for your C native dependencies is a dynamic library. And then you place that inside a directory structure that needs to respect the Python wheel format, zip it, create a zip file, and then you can upload that to the Python package index.
Okay, and you're uploading like something like a dozen different binaries in that one zip file.
Yeah, depending on how many targets you want to support. So that I would say is probably something interesting to do for people that are already doing this. So that will already be an improvement. But I think one can do even better than this.
Okay, go on.
So the whole point of building wheels is that you don't trust your source distribution, so your Python package plus C source files. You do not trust that thing to build correctly on your user's machine.
Yeah, which is fair. It probably won't.
Because it won't. Yeah, it's absolutely, like, it is absolutely rational to have that expectation. Now, but what if instead you could make it work? So just like we talked about improving the experience of building Python wheels for package maintainers, what if the same improvement could be instead brought directly to the user? So here's the idea. In a Python source distribution, you are able to define install time dependencies. So a dependency that the package has, not at runtime. So the package will not have even any dependency, any other Python package dependency to be able to load it in the interpreter. But you might have a dependency that is only required during install time as you are installing the Python package. Sometimes, there's some processing that needs to happen. One kind of processing that might need to happen is building C source code to obtain the dynamic library that I mentioned, like the final artifact. Now, the problem is, as we said in the beginning, if you're trying to leverage, to rely on the system C compiler, things are going to go wrong. But what if you could instead pip install ZigLang? So the idea is your users do not need to get Zig on their own. They don't need to do anything. They don't have to do anything. Instead, your package declares Zig as a dependency, have the Python package manager fetch Zig for you, and use it to run the build process in the same fashion that I just described, in the same way that Python wheel authors could do, but except you run that on the user machine directly. So now the user can reliably build source distributions.
Okay, so let me check I've got this straight. As a package author, trying to wrap a C library for something useful like machine learning, let's say.
Yes, for example.
I write my Python C bindings. I write my Python level nice API for people. I write a build.zig file, and I include ZigLang as one of my dependencies in my requirements.txt.
Yes.
And just ship all that source and dependency stuff. And now I expect my user to actually be able to reliably build C libraries without having to worry about it for their particular platform. And
exactly.
Just their particular platform.
Yes, you still have to do some work, right? You still have to get the build process right, like the C source code build process right, which is not immediately trivial. But I think you're now turning a intractable problem into a tractable one. So now you do that work once, and maybe you have to iron out some kinks, and maybe you discover, maybe you're not a, Windows user, and you discover that Windows needs a little bit extra care. But that's it. After you do that, people do pip install your package, while pip installs their package, it also pip downloads the Z compiler, which, by the way, I omitted this point, which maybe I should state clearly. The Z compiler has been packaged for Python, and it is available to anybody. They just need to do pip install ZigLang, and they get the Z compiler. And it's actually a legitimate way of getting access to the Z compiler if you want. I wouldn't recommend it over the other, official ways of installing the Z compiler, but it works.
Okay.
Yeah. And so you pip install the Z compiler. As the user is pip installing your package, pip also downloads and installs the Z compiler, and then it uses it during the installation process of your package. And if you got the build process right, it will work reliably for all your users.
Let me just be clear here. So is this hypothetical, like this is the way we could be doing Python packages, or is this, you could actually do this today this way?
You could do this today. You would have been able to do it for a while now. Like we have packaged, there's one contributor, White Quark. I don't know if this is a name that is widely known in the community in the Python community, or if so, to what degree. But White Quark has been very diligent in maintaining the the Python ZigLang package. And so, this is something that is perfectly doable already today. You don't need to ask anybody for permission. Like you can totally just do the work to make it happen for your package.
Okay. And the other thing, once I've got this working, right, if I did it this way to build my Python package to ship, do I still have to CI like a dozen different Zig build jobs to check it works?
Do you still need to publish wheels?
And also, do I have this CI process just to check that it's going to work on people's machines?
Probably it's not a bad idea. Yeah, it is not a bad idea. Another trick, if your point is like testing success, another thing that you could do is leverage Wine, and the other thing is, I think, Darling, which is how we do it in the Zig project. Like in the Zig project, the compiler, every time a commit is made and we run CI for the Zig compiler, all tests for the Zig compiler are run on the native machine, on the native target, but then they're also cross-compiled for Windows and macOS and run inside of Wine and Darling, respectively. So Darling and Wine, they're like emulators. Wine doesn't want you to call it an emulator, but I'll still use the word emulator. Yeah, right. So you can use them basically to run tests for those other platforms and see if things work out correctly.
Okay.
But then the question is, but then after that, do you still need to publish wheels? And that is a more complicated thing if you think about it.
I don't shy away from complicated questions. Why is that complicated?
Well, I would say that today people are not yet using ZigMatch for this. And so, yes, whenever you have a Python package that depends on C libraries, you have to build all the wheels that you can build, because otherwise you will get installation failures from your users. Once you perfect your source distribution, you perfect your building process, and then at that point, you don't need wheels anymore because you expect the build process to succeed on your users' computers. So you don't have to. You might still have a reason to do that, especially, or at least, let's say, mainly in the case where, for example, building the C library takes half an hour. That is the case, for example, for TensorFlow or for some other huge C dependency. In that case, you probably want to spare your users from the 30-minute long build process. And so you pre-build it for them. But in all other cases, which is not that uncommon, like there's, for example, some parsers that are known to be fast because they have the parser logic implemented in a native language and not in pure Python. And there's plenty of those things for all the common file formats. And they're like popular packages because people want to parse JSON, YAML, or whatever fast, oftentimes. Those are all packages where most probably, well, I would say almost definitely, the build process will take, 5 seconds, 10 seconds at worst. And so in that case, you don't need the Python wheel. You don't need it at all.
Okay. Yeah, okay. So, and this has a knock-on effect because this is how we first started talking about this topic. This, in your opinion, could have a knock-on effect to the people maintaining the Python package index.
Yeah, because I learned this. I actually don't remember how I stumbled upon this notion, but oh yeah, okay, I'm starting to remember. I joined a local meetup here where I um, met with some people who do a lot of Python work, and we ended up talking about how big the Python package index is, and we discovered there's a website that contains all these stats. The website is pypstats.org. Like if you just search for Python package index stats, it should be the first result.
I'll put a link in the show notes. Yeah.
Nice. And that website has a bunch of stats for the Python package index, and right now it's at around 85 terabytes of all total data that it stores.
Right.
And 75% of all that data, it's binary files. So it's Python wheels with a ton of redundancy, right? Because it's going to be the same project being built for all the combination of different CPU architectures, operative systems, plus different versions of the different operative systems, plus different releases of the Python package. Because if you make a new release of your Python package, right, you change something, which might be that you even just changed the Python code. You didn't change anything in the C code.
Right, yeah.
Actually, that most probably going to be the case. You still need to build all the wheels again.
Oh, yeah. So you end up with like a dozen different versions of binaries for every release, multiplied by all the many packages that Python has.
And if you look at the growth curve, is severely exponential, and and it's not going to get better, like, because the more architectures come out, the more you will still have to do this, right? ARM 64 used not to be all that common of a platform, but now it is. And there's also RISC-V that is trying to make waves, and more. So it's a big problem in my opinion. So to be clear, I don't speak for the Python package index project. I do not know their financials. And I do think that given that Python is like one of the leading languages in the tech industry, they probably have a way of making the economics of all of this work. And, they will also have sponsorships and support from big tech companies. So the clouds, so wherever they store this data, let's say it's going to be AWS S3. I don't know for sure, but let's assume. I'm sure that they will get free credits from AWS. But the growth is still there. The cost is still there.
Yeah, 85 terabytes growing exponentially. Sooner or later, you're going to hit that problem, right?
Oh, yeah. What's funny is that I applied. So I gave a talk on this subject, on this very subject that we're talking about at PyCon IT. And when I applied, I looked at the stats, and the total size was actually like 60 terabytes. Then 2 months later, I went to give my talk, and I was looking at my slides and like taking screenshots, right, of the latest data, and it was already at 87.
Right. So if anyone listening to this in 6 months' time is dealing with the package size emergency that's exponentially come out of nowhere, this is an answer.
Yeah. And I think that is an interesting opportunity also for the package index to do something that some other package ecosystems have already implemented, which is moving to like a cached model, where the idea is today, because of how janky and non-standardized is the process of building your C dependencies. This is another interesting perspective if you look at it from a from a more abstracted level, from a more like ecosystem perspective. Today, in the Python ecosystem, the process of building native dependencies is not standardized. It relies heavily on Docker containers, and every package author is kind of meant to figure it out on their own how to do it. To be fair, that's because that's the state of things in the C ecosystem in general. Like in the C ecosystem, you kind of also are meant to figure it out on your own how to build things.
Right.
But this unfortunate situation gets inherited by Python. And so today, if you delete a wheel from the Python package index, then it's not going to be that easy to rebuild that same wheel from the original source code, because you need to, spin up the same build environment that the package maintainer has, And again, it's not going to be standardized. So either you get them to tell you how to build their stuff, or the chances are it's not going to work first time, or like you're not going to be able to automate that process.
Yeah.
But if you're able instead to automate it and make it reliable and standardize it, which Zig would be one way of achieving that, then you can delete wheels. You can delete wheels once they stop being used by people. And so your exponential growth stops, because you can say, I'll devote 40 terabytes to cache all the most commonly downloaded wheels, and everything else we are free to delete whenever we are running out of space. So instead of having to keep around all the, because if you think about it also from the perspective of Python package versioning, obviously the latest version of a package will be more important than all the older versions, or maybe even the intermediate patch versions.
Yeah, as long as you can use the old versions, you don't need to have them like fresh and ready to ship. Right?
Yeah, you won't. Yeah. And there are some that are especially useless, right? Because maybe you still want to keep around major versions, older major versions of maybe even older minor versions. But like a patch version, according to semantic versioning, it doesn't matter all that much. Yeah, and they all have a weight. They all are going to be what you mentioned, like a dozen different wheels or even more. And being able to delete them would be, that would solve the exponential growth problem right away.
Yeah. I can think of, like, we've all seen a version, like someone releases version 2 of something, and then within 3 hours releases version 2.0.1.
Yeah.
You should never use 2.0.0. That was a mistake, right?
Yeah, absolutely. And right now, all of this stuff weighs equally on the package index, and you cannot delete it equally.
Yeah. Okay. So there must be not just the Python package index dealing with this problem. We've already mentioned banks, like large corporations often hosting their own stuff internally. They must be facing this problem perhaps more acutely.
Probably. When I gave my talk at the Python conference, PyCon IT, an attendee afterwards came to talk to me, and he was mentioning that he, from his perspective, like he really resonated with the way I explained like the problem statement, like man, you have to build all these huge combination of Python wheels. And he was saying, I spent like the last 2 weeks doing exactly that for our internal stuff.
Yeah.
And I think he didn't work exactly for a bank, but it still was some kind of financial intermediary, I believe. And private organizations also face the same exact problem. And if the Python, package ecosystem were to introduce a way of semantically caching these things, it would be nice, probably also for them.
Yeah, I can see that affecting any company that is large enough to have like a dedicated DevOps team or a dedicated build tools team. Right? Yeah. Okay, so the one big topic we need to get into that we haven't really touched is, I mean, in a way, we've just talked about Zig, not the language, just Zig, the build system. To be thorough about that, we have to talk about this design choice, which is Zig doesn't have make. It has Zig. The build tool is the language, right?
Yeah.
Tell me about that and how it plays out.
So the way it works is that Zig took interoperability with C serious since the beginning. I would say it is kind of a mandatory thing that you have to do if you want to be a systems programming language, because some of the most important systems out there today speak C, speak the C API, have C header files that they use as a way of interfacing with their APIs. Like we mentioned, the C standard library. The C standard library is, for some operative systems, the interface. It's the way you're expected to communicate with the operative system. And so you kind of have to do that. Or, you have to interface with C one way or another. You can decide to stay more away from it and maybe manually translate those header files to some other file format or use some other mechanism. But one way or another, you have to interoperate with it. So Zig decided to just bite the bullet and go all the way down and interoperate with C very deeply. which means that you can just directly C import C header files in your Zig source codes and source files, and then you can directly access those C definitions that you are getting from header files. So that works. Additionally, since Zig was relying on LLVM to build optimized executables, well, today Zig relies on LLVM pretty much for building all kinds of executables. But I guess the main feature that you get from LLVM is optimizations. LLVM is particularly good at that. Mm-hmm. So since Zig had to bundle that, it didn't really take much more to also bundle Clang. So Zig is a C and C++ compiler because it leverages Clang, which is why you can, Zig is not, how can I say, it's not hard to replace your current build process with Zig because you're still using a standardized, well-known, well-used, production tested C compiler. But on top of that, there's a lot of things that C compilers and in general C++ toolchains just do not do out of the box, which is support for cross compilation and some other minor things. But if you then think about cross compilation and how serious we are about it, then that in turn means that the build systems also didn't really rely on that much, or rather, I don't want to comment exactly on how well or ill-suited C build systems are to enable cross-compilation, but it is true that historically, C projects never use those tools to attempt to obtain cross-compilation capabilities. One way in which they always break the ability of a C project to do cross-compilation. So the idea is you see a C project that has like a make file, and you try to make and build a project and target another system. One way in which very often this type of stuff fails is because, for example, they have capability checks that check whether your system is able to do certain things or not. And that thing goes down to very weird extremes. For example, I'm thinking of, I'm familiar with Redis as a project. And if you look at what's inside the Redis makefile, you will see that at some point, the makefile asks itself the question of whether your C compiler supports C11 atomics. And so what it does is that it prints out a tiny test C file that tries to use these instructions and then tries to compile it and then tries to run the application, and it expects the application to run and return a successful exit.
Yeah. It's like duck typing on your C compiler.
yeah, they're duck typing your system capabilities.
Right. Yeah.
And projects that use CMake, usually, in my experience, building something that has CMake as a build system takes forever because also you spend a lot of time asking very basic questions. Like you see the CMake file testing for the capabilities of your C compiler, of your system in various ways, the availability of system, the presence of system libraries. And so it does all this testing. But unfortunately, I guess that made sense in the past, and it allowed the build process to basically be more reliable. And whenever something was missing, the thing would be able to, it would detect it early. And so it would be able to tell you that you needed to install an extra dependency, or like your toolchain, like your compiler was too old because it didn't support atomics or something. Or it could, at the very least, feature toggle in the C process. So like you don't support atomics, fine, you can still build the process, but then a different macro will be selected in the C source file, and then basically the C program will work out, just not relying on C11 atomics. So they can also do that. But the problem is that then if you want to do cross compilation, this approach is inherently flawed because you don't care as much about the capabilities of your current system. You care about the capabilities of your target system.
Yeah.
And so, long story short, Zig pretty much wouldn't be able to achieve what it wants to achieve by using one of the commonly used build systems. So, by being a project that wanted to tackle things bottom up, it then decided to also be a build system. And to be a build system that also is able to build C and C++ projects, since we said that Zig is also a C++, C and C++ compiler, then you also need the build system to be powerful enough to account for all the weird things you need to do to build C and C++ processes, which includes like running sometimes, configure step, but there's also some other like more bespoke things that certain C projects do. And so the Zig build system is capable of accounting for all of those. Like you can basically the Zig build system is able to run any kind of executable at build time as part of your build process, cache the intermediate artifacts, and then have those be used by subsequent build steps, because that's what you have to do.
So the decision to use Zig as the build language rather than creating something called ZigMake, right?
Yeah,
was driven by your assessment that this is so complex you actually need a whole programming language to tackle it.
I think that ultimately, to answer this question, precisely and fully, to understand what was the intent behind the design of Zig, the only person who knows fully would be Andrew Kelly, who actually did the work of designing it. But I can say I can make some statements that I have good confidence are true enough. So it is absolutely true that you could have a declarative syntax to make happen the same exact things that you can express the same things that you can express with the build.zig file, which, yes, is written in Zig and thus can leverage, you can do everything that you can do in a Zig program. So you could obtain the same result by using a declarative syntax, like basically writing a, make alternative for sure. That said, I do tend to agree with what you said, which is that it can get so complicated that having the ability to express things, in an imperative fashion can bring some advantages. I have to admit, I personally have learned how make works at least 10 to 15 times, because I would learn how it works, then not use it for like a year, and then come back to it and forget how all the things are connected, and then have to relearn it again. Like I've gone through that process quite a few times.
I think I got the idea behind make very quickly, but I have to go and look up the syntax every single time.
Every single time, yes. Yeah. And in general, Zig is a language that tries, it's a project that tries to, maintain simplicity and not introduce new syntax, new things, new machinery, unless it really gives you a very good bang for your buck. So in a sense, since this could be pulled off with the main language, there wasn't a need to implement another alternative to make. So follow the same steps that make took. Lastly, the Zig build system is still, even though you write your build script in an imperative way, what your build script does is declare a build graph. So it still has ultimately the same properties of using what you get out of a makefile, in the sense that a makefile declares a build graph, and then by doing that, the build system is able to parallelize if you want, or like understand what depends on what, which in turn can also allow you to skip build steps. Like if a build step depends on certain input files that have not changed, then you can reuse the artifact that was built the last time. You don't need to rebuild it again from scratch.
Okay, so you have modeled the same semantics.
Absolutely, yes. Yes. And because the build script is not actually doing the building. The build script is using an imperative language, but it still defines a build graph that then will be run by the build runner. And so actually there's also a funny project that is a alternative build runner that was made by the Z community that doesn't run your build. It only plots your build graph as like an image.
Right.
Because you can analyze the build graph and reason about it.
Yeah, so you turn the build recipe into data, and then you can turn that data into different things.
Yeah. And there is one last thing that the thing that I think to me is the most amazing thing of the Zig build system. So still talking about like differences between Zig and like why not just make use of make, since it's already exists and it is standardized. People who have used make have all had to learn this. Sometimes because somebody told them, sometimes they had to learn it the hard way. But with make, projects tend to have a clean step. or maybe even more than one. So you have make clean or make dist clean. And those steps remove cached artifacts. Have you ever had to use those commands?
So many times, usually because I don't know what's going wrong and I hope that make clean will fix it.
Yes, this happens all the time. Okay, the problem here is that the caching model that make uses isn't perfect. It has some flaws, and that occasionally causes your cached stuff to go out of sync. So some of the caching process doesn't reflect anymore the state of your source code. And so two artifacts that would both need to be rebuilt, maybe only one of them gets rebuilt. And so something goes wrong then later at the linking stage, which is at a point where you as a normal developer, you have no idea how to fix it because you don't know, like, oh, this symbol is missing. And so you don't know. And so you run make clean. Well, here's the best feature of the Zig build system. It doesn't have a clean command. The Zig build system does not have a clean command.
That's either confident or foolish, and I think you're going to argue it's confident.
Yeah, you don't need it. You don't need it. So like every other software project out there, obviously it might have bugs in it, and it might be that if you trigger that bug, you will corrupt your cache folder and you might have problems. So obviously I'm not stating, the impossible, that our software is already perfect.
Okay, but tell me about the deeply improbable.
But as a build system, as a build and caching system, because yes, the Zig build system also performs caching, it is sound. So you don't get your cache going out of sync, out of whack, for no reason. And so it is not a thing in the Zig community to tell people run Zig build clean, because it doesn't exist. Occasionally somebody, maybe, I'll tell you maybe one example that I've actually seen. Somebody at some point changed their version of Zig. So they built their project with an older version of Zig. They updated to a newer version. And I believe that there is like a unique seed that needs to change between different versions of Zig to make sure that basically that seed basically identifies the Zig version compiler, so that according to the cache system, an executable built with an older version of the compiler looks like a different artifact than the same thing built with a newer version, right? And I believe that maybe somebody forgot to update that thing or something similar happened. And yes, we did tell somebody, you know what, try to delete the cache folder and see if it works again. And in that case, it happened. But in all other cases, you don't clean your cache. There is no reason to do that. There is a blog post that Andrew Kelly wrote explaining exactly the lengths he goes to make sure that works. And it's a lot. Like, you have to do a lot of work because you have to understand exactly what guarantees you can get from the OS in terms of being able to observe when a file was changed last and how that interacts with deeply, arbitrarily deep directory hierarchies, which is another thing that is a problem every time you have to deal with the file system. That plus other concerns, and you will see why the Zig build system doesn't need a clean command.
How is the cache working? Because I'm thinking Make's caching system, in quotes, was largely look at the timestamp of the thing you're building and the thing you want to build from it.
Yeah.
And if the timestamp's newer, then you bother to rebuild, and that's it.
Yeah, in Zig, it's more nuanced than that. It's the timestamp. It's the inode, I believe. It is also the hash of the file. And there's also a way of detecting if the system is not giving you the right level of granularity when it comes to timestamps. So there's also a notion of, yes, this timestamp has changed or is newer, but it's not newer enough to really count as a cache hit. And so we should count that as a cache miss anyway because of the imprecision of the timing stuff.
Right.
So if you want, I'll give you a link later if you don't mind sharing it with the audience. I don't remember all the details, but there is a lot of things that you have to do to get that stuff right.
Okay. So we can make this more concrete. by fulfilling the promise of coming back to how you build Zig for Python.
Oh, yeah, no, that's the interesting thing. That what I mentioned is not building Zig for Python, or rather, if you want, we can talk about it, but it's actually fairly mundane. If you go to the Zig organization, you will find I think it's called Python or PyPy. I think it's PyPy-Zig. In any case, you will find a repository that contains the process to build those Python wheels. By the way, we do ship the Zig compiler as a Python wheel. We do pre-build it for all the targets, because if we didn't, well, first of all, we are in the unique case where we are Zig, so we cannot depend on Zig like other projects
Right.
could, right?
Yeah.
Or at least it's not that simple. But setting aside that quirk, Zig today depends on LLVM, and building LLVM takes like half an hour. So we are in a situation that, if you will, it's roughly similar to like TensorFlow, where the idea is we probably shouldn't inflict that build process on the user. And so we pre-build everything ourselves.
So you're shipping wheels for time's sake, not for reliability's sake.
Exactly.
Yeah.
Plus, I would say the problem that pulling off the first Zig package, would have required us to build from source, pre-build anyway, because at that point we didn't have any ZigLang package on the Python package index that we couldn't rely on.
Zig's all the way down.
Yeah, but in the organization that I mentioned earlier, the one called All Your Codebase, we have a Python compiler, a Python interpreter build.zig. So it's a build.zig that allows you to build CPython. And what's interesting about that is that it builds a fully static CPython. So this might not be a need that is super common, but occasionally people might need to, have a build of the Python interpreter that is like reliable, self-contained, that then can embed in a bigger system. And in this case, Andrew wrote and maintains that build.zig file because he has a music server project. I don't know if music server is the right word for it, but he basically has like a system where you set up an instance of his music player on your local network, and then all your computers can access it through the network. It has like a web interface, and you can play music on whatever computer on your network that you want.
Oh, like peer-to-peer music player.
Yeah, exactly. But I guess the intended usage of it, in any case, is like private stuff, not public. But yeah, and he uses it. It's called Groove Basing. And what's funny is that there's a interesting amount of people in the Zig community that actually knew Andrew because of Groove Basing, even before they knew him because of Zig.
That's an unusual way to advertise the project.
And but I think he builds it because he uses it a lot. Like, he just likes to listen to music while he programs. So anyway, the point is that is a project that depends on a Python interpreter. He wants to have access to a Python interpreter, and so he created a build.zig file to build the entire Python interpreter statically, which is interesting. So it's a static build of CPython. And what's nice about it is that it's going to work on all Linuxes. Most people will not have that need, but I think that some will understand how nice it is to be able to have a truly portable build of the Python interpreter. No matter where you toss it, it's going to work.
Right, yeah. The one that springs to mind immediately is when you want Python, but you don't have permissions to install it.
Yeah, that's a good one. Yeah, that's a good one. Or maybe you want Python in your NixOS, or you want Python in your on Alpine, or some, you just want one Python that you can reliably toss around, and it's just going to work. Like that's embedded devices, maybe not super tiny. Obviously, we're talking about the Python interpreter, which requires a certain level of resources. But point being is that what's interesting about this setup is that it's a build script that you can inspect and take a look at what it does to build a serious C project. Because obviously Python is a serious C project, and it works beautifully. You just do zig build and it works.
Okay, then that leads me to my final question. I think I have to ask: if someone were building C or C++ projects, and was happy and had no interest in switching language, would you make an argument for switching build system to Zig?
I would. I would for two reasons. One is that in reality, most C and C++ projects tend to have more than one build system because of just it's kind of like the Wild West, the C and C++ build ecosystem, because people have preferences. Some people want to use Make. Some people want to use CMake. Some people use Make and don't want to use CMake ever. Or some people are tired of Make and they want to use Ninja. And some people are on Windows and they say, "What can we please build this project? Can we please have a batch script or a PowerShell script?" And so in the end, you end up with this soup of things, because understandably, like let's say that you even have like one sh file, like a bash file. Well, a bash file, it's not going to run on Windows natively easily. So people on Windows, what are they going to do? So using the Zig build system means that you get rid of all of those. You get rid of all your dependencies on all these build systems, and you just have one dependency. And that one dependency can be both your C compiler and your build system. Just one dependency to solve all these problems all at once. The second reason why the Zig build system is interesting, we didn't mention this much yet because it's still not yet fully complete. It's still a little bit work in progress. But the Zig build system is also package manager. So that means that your other dependencies, so like it is obviously common for C libraries to also have other dependencies. Like you can imagine that you have like a curl, for example. I would imagine it depends on OpenSSL or some other SSL implementation, and et cetera, et cetera. And the Zig build system can also fetch those dependencies. So we don't have a fully fledged implementation yet with all the bells and whistles that normally people expect from package managers. But the simple act of declare in a file that you want to depend on another package, on another library that has a build.zig file, and being able to access what's in that build.zig file so that you can build a dependency and then link against it or use it as a tool during your compilation process, that already works. And that means that you have solved another problem, basically, because now it really is just Zig build and it works, and you don't have to depend on anything on your system.
Yeah. I remember this reminded me a couple of years ago, I had to write some documentation for using a library in a few different languages. And when it came to writing the C one, I just hand-waved the whole problem away. I said, you will need to have these libraries pre-installed as prerequisites.
And it's annoying. It's annoying. And to be fair, you can still do that with Zig. So it's not like with a Zig project, you cannot depend on system-wide things. You totally can. Like the type of integration that C projects tend to have with the system, you can absolutely have with Zig as well. Zig understands, if you have like your build essentials installed, Zig understands how to query the system for where libraries are stored and all that kind of stuff. But the key point is you don't have to. And the system, the Zig build system, or in the Zig ecosystem in general, allows you to be fully self-sufficient. And full self-sufficiency means that you can reliably do just Zig build. If you want, I have one last funny example of what you can pull off with the Zig build system. I am working on a static site generator because I've talking about Node GYP and talking about annoyance when C build errors. I used to have my personal blog written in Gatsby, which is a Node.js framework, but it does have some C dependencies, some native C dependencies, because Node, JavaScript, or like Ruby, plenty of those high-level programming languages are in the same boat as Python. They all have native dependencies. So my blog, funnily enough, was the only software project that I couldn't move to my new ARM M1 Mac because the build would fail and I didn't know how to fix it. Yeah. So that kicked off basically a cascading search on my part to find another static site generator, and ultimately led me to the point where now I want to write my own. I'm so opinionated that I decided to bite the bullet and make one that I really like.
A great many people hit that point.
Yeah. But here's what I did. I wrote it in Zig, obviously, because that's what I do. That's what I'm used to. And my project it's mostly Zig source code that I wrote, but not entirely. I do depend on 3-seater and a C implementation of a Markdown parser. So, which is very common. It's like the CMark Markdown parser. I believe it's like, I don't know if it's truly official, but it is the de facto parser that everybody uses. What's nice is that I depend on those C libraries. They all have their own build.zig file. And so I don't care about that anymore. So they're basically become a non-problem because I just run Zig build and they work on all systems. So that has been solved. I literally never, like in the beginning, I had to maybe, fix some things. People would report build errors, but it's been months and nobody ever gets build errors from those. But the thing that's funny is that the entire static site generator system itself is actually not one program that does this work, but it is a collection of tiny tools that are orchestrated by the Zig build system. So your markdown files, your HTML templates become source inputs to a Zig build graph that my static site generator orchestrates. And those then go through a build process where the output, well, you would normally use the Zig build system to build a program ultimately. Like we mentioned, building shared libraries when building native dependencies for Python projects. But in my case, my final outputs are built HTML files and CSS files and static assets for the website.
Yeah, because that's all a static site generator is, right? It's a compiler that compiles to HTML and CSS.
Yeah, exactly. And what's funny is that since I define the build process for your static site through the Zig build system, I automatically get for free caching. So if you don't change a markdown file, it doesn't get rebuilt because the cache already has the cache version of that artifact.
Okay, we're gonna have to stop before I decide to move my blogging engine to yet another tool.
It's a bit early, so to be clear though, it's a little bit early. I am serious about it, and my next goal is to make it complete enough that we can move the official Zig website to it. Currently, the Zig website still gets generated. It's a Hugo project, but the plan is to have my system be complete enough to do that. I'm not there yet, so it's not like production ready.
That'd be a nice bit of dog fooding though.
Yeah, but we're getting there.
Is the source available if we want to take a peek at Loris Cro's handwritten Zig?
Absolutely, yes. It has a website. It's zine-ssg.io.
Okay, I'll put a link in the show notes. And on that, I should probably let you get back to it.
Loris,
thanks very much. That was a really interesting dive.
Thank you, Chris.
Thank you, Loris. So if you want to see how this works out in practice, I'll put a link to the zine source code in the show notes. As he said, it's not ready for production, but it definitely gives you a flavor of what a serious Zig build script actually feels like. And if you want to learn more about Zig generally, there are links in the show notes to the Zig homepage and the previous episode we had with Loris, where he went through the language features of Zig and what makes it interesting as your primary language. While you're heading down towards the show notes, should you pass a like button? Consider clicking on it if you've enjoyed this episode. Why not glance meaningfully at the share button if you've got a friend who you think might enjoy it? And if you want to support future episodes of Developer Voices, click your way across to Patreon, where you can actively support the channel, get backstage updates, and help me keep finding new guests for the long term. We'll be back next week with another brilliant technical mind, so make sure you're subscribed, and I will see you then. I've been your host, Chris Jenkins. This has been Developer Voices with Loris Cro. Thanks for listening.